All right, I'll start here. So now we start with clustering methods that are used in genomics. And I first give you a background on clustering. I'll talk about partitioning around medoid clustering and hierarchical clustering. There are many very good textbooks for clustering methods. So why do clustering? So historically, of course, objects are clustered into groups. For example, the periodic table in chemistry or taxonomy in biology. By clustering things into groups, we hope to arrive at an understanding of the data. So we want to see the global structure of the data. In other words, we want to see the forest for the trees. In biology, we may want to detect heterogeneity in the data. For example, when we start with a large cancer data set, we may want to find different tumor classes. But also, one can, of course, cluster genes. Let's say you have 50,000 genes, you can cluster them into different groups. Why? Because they may correspond to biological pathways or different cell types and so on. Another goal in cluster analysis is to find data outliers. Things that don't cluster together with other things may be outlying. Now, there's a fundamental difficulty in defining what is meant by a cluster. So here I show you point clouds in the Euclidean plane, and roughly speaking, then the first plot shows the three distinct clouds of points, and so I think most of us would say, well, these are different cluster of points. So there are three clusters. Moving to the next plot, we already have a problem. Well, are there two clusters corresponding to these three, to the two endings, or is it one big cluster that is linked? There's no right or wrong answer. It really depends, you know. There are some clustering algorithms that will say there are two clusters, and then there are other methods that will say, no, there's only one cluster. It gets even worse for the third example. Question, is it one big cluster, or are there four different clusters, or are there two clusters? It depends, you know. And this already shows you one thing. Clustering is a little bit of an art form. You as the data analyst, you need to use your subject knowledge to make intelligent choices, not arbitrary choices, informed choices, saying, well, in my particular application, this last plot indicates there's only one cluster, or in my other application, I really expect many clusters that are loosely related, and then you could say, well, maybe there are four clusters, you know. So we can cluster genes in order to find, for example, genes that are co-regulated. And another term for cluster in this context is often module. So sometimes people talk about gene modules, and they really mean gene clusters. We can also cluster samples, for example, human subjects, again, for tumor class discovery, for example. But also one can cluster both rows and columns at the same time, meaning genes and samples, and these are known as bi-clustering approaches. There's a vast literature on all of these topics. Now, the input of many clustering algorithms is a dissimilarity measure, and a dissimilarity is, of course, just the opposite of a similarity measure. What is a similarity measure? The similarity measure indicates the strength of a relationship between two objects, for example, two subjects. For example, if you have a Pearson correlation coefficient between two subjects, you can take the absolute value, and that is a measure of how similar two subjects are. It's a similarity measure. The other example, in order to relate a similarity to a dissimilarity, you can sometimes use just similarity equal to maximum value minus dissimilarity, you know. Just be aware of it when these terms, similarity versus dissimilarity, are highly related. Now, it turns out that although similarities and dissimilarities are highly related, it turns out that we usually input a dissimilarity measure into the clustering algorithms. So most R functions that we use for clustering require that the user input a dissimilarity measure. So what's a dissimilarity measure? A dissimilarity measure could be a distance, right? A Euclidean distance. How far away are two objects? That measures in certain ways how dissimilar they are. Now, a dissimilarity measure can be a distance, but it doesn't have to be a distance. In any event, there are many types of distances: Euclidean distance, Manhattan distance, and so on. So let me now describe what is known as combinatorial clustering algorithms. There are two famous examples: k-means clustering and partitioning around medoid clustering. So what's the idea? So what we do is we start out with observations that are, of course, labeled by an integer, and we want to cluster them into clusters that are also labeled by integers, meaning cluster 1, cluster 2, cluster 3. And the cluster assignment is then a mapping where the ith observation gets mapped to the kth cluster. So this C is known as the encoder. It encodes where each observation lands, in what cluster it lands. And now, what one usually does is one looks for a particular cluster assignment or encoder that minimizes a certain loss function, or also known as energy function. For example, you may define the following loss function based on a dissimilarity measure. This is, let's look at it. So the idea is very simple. You look at all pairwise dissimilarities between the objects that are in a particular cluster. Okay, you form, let's say in cluster 1, you look at all pairwise dissimilarities and sum them up. Well, what do you want? You want a cluster so that all the objects are as similar as possible, meaning the sum of the dissimilarities should be as small as possible, right? You want that for cluster 1, you want that for cluster 2. And so this loss function measures the sum of dissimilarities among objects in the same cluster, you know? And that's known as the within cluster point scatter. It measures the scattering in certain ways. And yeah, so what would then be an optimal clustering assignment, an optimal cluster algorithm? Well, it would choose this encoder, the cluster assignment, in a way to minimize this loss function. So why? Because you want that all objects in the same cluster are as similar as possible. And so one way to then accomplish it is by literally enumerating every single cluster assignment, calculate this loss function, and simply choose the encoder that minimizes that. However, this is a computationally very hard and challenging problem, and therefore people developed strategies based on iterative greedy descent, for example. You know. A very famous combinatorial algorithm is k-means clustering. Now, it has one major limitation, which I already highlight here. It really is based on the Euclidean distances between objects. Remember how I defined here this within cluster point scatter, the loss function, for a general dissimilarity measure, any. Whereas in k-means clustering, we assume that this dissimilarity is the Euclidean distance. And then what the user has to do is they have to pre-specify, well, how many clusters do I want? That's the parameter k. And then you may have starting points for the cluster centers. And then what the algorithm does is it iterates between cluster assignment and reallocating points to find a cluster assignment that leads to the lowest within point scatter function, you know. So that's k-means clustering, you know. There is another algorithm that is similar in spirit called partitioning around medoids clustering, and its advantage is that it takes as input any dissimilarity, not just Euclidean distance. And again, same logic. It minimizes the within point scatter using this greedy algorithm. So this method is called PAM, partitioning around medoids clustering, or also known as k-medoid clustering. Do you guys have any questions at this point? What is the problem with these methods? The problem is that the user has to specify how many clusters do I want. That's the number k, critical parameter. And let's say you have 50,000 transcripts. Do you really know how many clusters there are? You know, are there 50? Are there 500? Are there 5,000? That's a hard problem. Now, statisticians have, of course, worked on estimating the number of clusters in a data set. But the truth is, people don't really use these methods in genomic applications. They don't work well, you know. And therefore, we now come to a different topic, which is hierarchical clustering. In hierarchical clustering, you do not have to specify the number of clusters. It's a major advantage of it. So many of you may have seen these types of plots. This is a heat map visualizing gene expression levels. And here you see these bizarre little structures, the rows and the above the columns, and these are known as hierarchical cluster trees, you know. And so I will talk about that now. These cluster trees are also known as dendrograms. And as I mentioned, they avoid the pre-specification of the number of clusters. And now a tree can be built in two ways, bottom-up or top-down. But here we only look at bottom-up approaches. So known as agglomerative hierarchical clustering. So how do they work? Well, they start out considering each observation as a singleton cluster, and then at each step they merge things, they combine things, you know. Every for example, gene starts out being separate, and then it merges the two genes that have the lowest dissimilarity, connect them. Next, it asks, well, what is the next group of two genes that has the lowest similarity? Now it merges them. Then it merges, and at the end, everything is merged. Let me come to an important concept, which is a measure of intergroup dissimilarity. The drawback of hierarchical clustering is that the user needs to specify what is meant by the dissimilarity between two clusters. Why is that? Because remember, the algorithm is based on merging and combining clusters, and that step involves measuring the distances between clusters. So the user needs to specify that. Let me explain the idea. Assume there are two groups of points, cluster 1, cluster 2, the blue dots and the red dots. And what can I do? Well, I can form pairwise distances between these points, right? And the goal now is to determine, well, what is the distance between the blue cluster and the red cluster? And one way to do it is to simply form the average, right? You have all these pairwise possible distances and you form the average distance. That's a reasonable approach. But you could do another approach. You could say, well, what is the distance between the two dots that are closest to each other? This minimum across all pairwise distances. That would be another approach. Or to form the maximum, which seems silly, but people do it. And so in any event, these intergroup dissimilarities are also known as linkage methods because they link clusters with each other. And so as I mentioned, there are these major types of linkage methods. The one I mentioned is based on the average, known as average linkage. You can form the minimum pairwise dissimilarity, that is known as single linkage, and you can form the maximum dissimilarity, that's known as complete linkage. And so when you want to use R to accomplish these approaches, or to implement these approaches, you use the methods argument in the hclust function. So so there's an R command called hclust that inputs a dissimilarity measure, and then you say, I want average linkage, you know. Or for the single linkage, you just use that type of code, you know. Now, let's compare the different linkage methods. So single linkage, based on this minimum, has the tendency to combine observations that are linked by a series of close intermediate observations. And so that produces this effect of chaining. Complete linkage does the opposite. And so it's a good algorithm when you have very compact clusters. So then the clusters look like the pearls on a string because it partitions elongated clusters into separate clusters. In general, we prefer average linkage for several reasons. Whenever you form an average, you really get a robust measure, right? In contrast, looking at the minimum intergroup dissimilarity or the maximum in pairwise distance, this is really cannot be robustly estimated. You know, outliers have a strong influence on these estimates. So therefore, we prefer average linkage. Having said this, R implements a host of different methods, so you could explore that. Let me now come to an important topic. How do we create a dendrogram, a cluster tree? Here I have a toy example where I have different numbers. The numbers are 1, 2, 3, 8, 10, and 12. And I want to cluster these numbers, you know. Now, as a human being, I hope you recognize there are two clusters, small numbers and large numbers, you know. The small numbers are 1, 2, 3, and the large numbers are 8, 10, and 12. But how do we construct a cluster tree based on that example? Well, the first thing you need to specify is the dissimilarity measure. And how do we do that? Or how do we define that? Well, we measure the dissimilarity between two numbers by taking the absolute difference. So the dissimilarity between 1 and 2 is 1. And you notice that here the two numbers, 1 and 2, get linked at the y-axis label of 1. Do you see? Because the y-axis, which is known as height, the height of the tree, specifies that as average dissimilarities. You know. So as I said, the dissimilarity between 1 and 2 is 1, so they get merged at that height. The dissimilarity between 8 and 10 is 2, so they get merged at 0.2. Now, the tricky thing is to decide how far are the numbers 1 and 2, this cluster, how far is it away from the number 3? Well, the average distance is 1.5. And there it is. Now, if you ask what is the distance between the numbers 1, 2, and 3 versus the cluster comprised of 8, 10, and 12, that distance will be 8. And that's why these clusters merge there. Do you see? So the cluster tree tells you about pairwise distances, or the distances between clusters. Now this was, the left panel shows the results for average linkage. The middle panel shows it for complete linkage, meaning based on the maximum pairwise distance, and this for single linkage. Before I move on, I just want to make sure that every single person in the room gets this. Do you get it? Okay. Because later we will have genes. So we will have cluster trees comprised of 20,000 genes. But the logic is always the same. You merge them according to how dissimilar they are. So if the dissimilarity is small, meaning they are very similar to each other, then the branch is very low down. Yeah. All right, so how do we create cluster trees in our R tutorials, which I will present later today? So this is a hierarchical cluster tree of, I want to say 4,000 genes. And notice suddenly the tree looks nasty. There are these, it has branches, and each branch corresponds to a cluster, right? Remember, hierarchical clustering is a clustering procedure, meaning you get clusters. However, hierarchical clustering first results in a tree. So how do you take a tree and turn it into clusters? Well, you do that by cutting branches. That's the idea, Coming back to the earlier example, how do we get clusters from this tree? Well, we cut the branches. We cut it here and say, these numbers are cluster 1, and these numbers are cluster 2. So we need a cutoff to decide that, to cut the branches. And similarly, in this more complex example, each cluster corresponds to a branch, but now we have the challenge to cut the branches. And I will teach you how to do that. There's R code for that. But then it turns out to be a good idea to again label clusters by integers, meaning cluster 1, 2, and 3, and often the clusters get assigned a color. For example, here is a big branch, and this branch corresponds to the color yellow, meaning we assigned it the color yellow, and then we say this is the yellow cluster, or this fuzzy branch corresponds to the genes in the blue cluster. You can also cluster vectors. So these are different vectors, and where the distances between these clusters reflects 1 minus the correlation of these. So I will show you how to create this plot. What is noteworthy is that this is a hierarchical cluster tree, but right underneath it, I visualize the underlying dissimilarity measure. Remember, the input of hierarchical clustering is a dissimilarity, and here I visualize it, where red indicates they are very close to each other. For example, these two vectors, notice the merging point, the height on the y-axis is low, meaning they're very similar to each other. And therefore, when I visualize the dissimilarity, there's red, meaning they're very close to each other. Similarly, here I have another branch, and this branch contains 4 different vectors, and again, they are very similar to each other, and that's why I get this block. So sometimes people not just visualize the hierarchical tree, but right underneath it, they visualize the corresponding dissimilarity measure. We'll revisit this in the afternoon. I just prepare you for it right now. Let me also mention that these methods are, of course, often used for finding outliers. So, for example, you can form the Euclidean distance between microarray samples, and then you can cluster the microarray samples. So in our R software tutorial, we will produce this hierarchical plot where each little leaf corresponds to a mouse. So these are female mice. And we cluster the mice in this hierarchical tree. And what we observe is there's one mouse on the leftmost mouse, mouse number 221, that is very far away from the other mice. Why do I call it far away? Because notice the merging height is high, much higher than where the other samples merge. So this mouse, something went wrong with this mouse. It may data quality issue, it could be that we have the wrong tissue, it's not liver tissue but muscle tissue, and therefore we may want to remove this mouse from the analysis because it looks suspicious. All right, just to wrap things up, so I reviewed partitioning methods and hierarchical clustering. The advantages of partitioning methods are that they satisfy some optimality criterion, right? You minimize a loss function. They are also very intuitive. While you group things together if they are very similar to each other. And also what I don't mention here is they actually turn out to be highly robust. The disadvantages are you need to specify the K, the number of clusters, and that's a major limitation in many genomic applications. And the second big disadvantage is that they perform poorly when you have what we call singletons, meaning often objects actually don't form clusters, right? So let's say you have your 50,000 genes, and let's say 20,000 of them can be grouped into clusters, but the remaining 30,000 are background genes. These genes are not even expressed, they do nothing. And they really form what we call singletons. They are separate. Now, if you have a partitioning method, then often these methods struggle with that. They will take these 30,000 background genes and just shove them into clusters. Why? Well, because you told them there are 50 clusters, and so they shove them into these 50 clusters. And so that's another major disadvantage of partitioning methods. Let's look at hierarchical clustering. Great advantages include fast computation, no need to specify the K, and it works very well with singletons. Why? We just leave them out there. The singletons are not part of any branch. But what are the disadvantages? The cluster tree topology, meaning the tree, is not really robust. So it could be that slight changes in the data lead to different branches. And so people really criticized hierarchical clustering over that aspect. And so what you would like to do is you would like to have a method that combines the advantages of partitioning algorithms with those of hierarchical clustering, meaning it has the robustness of partitioning methods, but it also has the advantage of hierarchical clustering in that I just mentioned. And the good news is we have such a method, and that is called the dynamic tree cutting hybrid method. This is a method that really combines partitioning around medoids clustering with hierarchical clustering. And this is implemented in R, and I will show that to you after the break, so we'll get to that, I briefly want to mention some R functions. So there's the cluster library. I also mentioned there's this R function hclust, right? This hclust function. But can you believe it? when people implemented hierarchical clustering in R, meaning in the H-cluster function, they made a coding error, you know. And so, fortunately, Peter Langfelder revisited the code and found this coding error and corrected it. And so now there's an R function called flash clust, which has the identical output as H-clust, completely identical, except that it's much faster, you know. So if you have large data sets, I urge you to use flash clust. K-means clustering is implemented in the R function K-means. And also this dynamic approach, which I mentioned later today, is implemented in the dynamic tree cut function. And finally, as you know, I will present a set of lectures on weighted correlation network analysis, which is really a very good package for addressing a lot of analysis tasks in clustering. For example, hierarchical clustering, but also how to evaluate whether clusters are preserved between a different data set. Because that is a very important task to check whether the cluster that was found in one data set can also be found in another data set. And to do that, you need what we call module preservation statistics. So later today, I'll teach you that. And finally, it's very attractive to have measures of cluster membership. You really would like for each gene to know how strong is the evidence that it's part of cluster 1 or cluster 2 or cluster 3. These are cluster membership measures or module membership measures. And later I teach you how to calculate them as well. All right, I guess we stop here and enjoy your lunch. And then when do we resume? Does anyone know? Yeah, 1 o'clock? Okay, let's make it then 1:10 so that you have an hour for lunch, you know. Yeah, did you have a question? Yeah, okay, thanks. So at 1:10 I see you, yeah.